Hello, and welcome to this film, which is all about non-octet molecules. It's another one of the high-level bonding films, and we've been looking up until now at how the shape of a molecule can affect its polarity and its intermolecular forces. But we've been focused just on molecules with 4 charge centers, so that is to say octet molecules. What we're going to do now is look at molecules that seem to have too many electrons around that central atom, and you don't need to know about these for the standard level exam, but you certainly do for the higher level exam. So hopefully you'll know the names of some of the different shapes of covalent molecules with 5 charge centers. The next film coming up deals with ones with 6. This is a good one for all the people with good memories out there. It doesn't really require a lot of understanding, it's just a bit of memorizing some facts, okay? And you'll understand what bond angles these molecules will form. So we'll be able to consider our VSEPR and apply it to these. Okay, we're going to start with one that you most definitely have to remember. So there are some shapes that you have to remember specific examples of, and the trigonal bipyramid is one of those, okay? If we just have a look at what we've got to have in order to end up with a trigonal bipyramid, we've got to have 5 bonding pairs of electrons around our central atom, and that's what you get if you draw an electron dot diagram for PCl5. It seems as though you've got too many pairs of electrons there, but the good thing about phosphorus as far as bonding is concerned is that it's got d orbitals that are very close in energy to these to its 3p and 3s orbitals, so it can actually use them to store a few more extra electrons, to put it in quite simple terms. Why is it called a trigonal bipyramid? Because we've got a trigonal pyramidal shape up there, and we've got a trigonal pyramidal shape underneath there. Okay, so there's 2 trigonal pyramids, one on top of the other. What sort of bond angles are we going to expect here? Well, if we try and fit this into a sphere, and we say that it's a bit of an egg-shaped sphere, but anyway, if we say that these 2 atoms are at the poles, then we can see that this is a 180-degree bond angle. If these atoms here are on the equator of our sphere, then they must be getting as far away apart from one another, and they must be 120 degrees. So this bond angle here is a right angle, it's 90 degrees. This one there is 120 degrees. And we should remember this shape and PCl5 as an example of this shape. And I suppose what that shape comes about as a result of in terms of electron pairs. Here's a seesaw shape, okay? This isn't one that you need to remember a specific example of, but you do need to consider what's happening to the bond angles when we chuck in a lone pair here. So if you were asked to draw an electron dot diagram of SF4, which you could be, even though you're not expected to remember that SF4 is an example of a seesaw, you'd end up with this kind of Lewis or electron dot diagram. You'd now have a lone pair here on the equator of the sphere, so I kind of got to turn my sphere over a little bit and make it even more of a strange shape. We've now got the equator going around here, and these were the ones at the poles. Looks like a horrible mess, but I'll get rid of it. So that lone pair, remember, lone pairs repel bonding pairs more than bonding pairs do. So all these bonding pairs end up squashing a little bit, and this angle in here is no longer a right angle, but a little bit less than 90 degrees. And this angle here is a little bit less than 120 degrees. And you don't have to put figures to these, you just have to say, well, that angle will have shrunk and that angle will have shrunk, so they'd be smaller than whatever they would be in the trigonal bipyramid. So it's a seesaw, it's called. Now again, another shape that you don't need to know a specific example for is the T-shaped molecule. You ought to be able to draw the Lewis diagram for something like ICl3 if you're asked, and you'd end up with iodine surrounded by 3 bonding pairs and these 2 lone pairs now. So now around our equator, remember, because we had the 2 at the poles, so maybe I'll highlight these in blue. These were the 2 atoms at the poles. We've got the 2 pairs of electrons at the equator, and they're squashing all these bonds together because they repel the bonding pairs more than the bonding pairs did, and so this angle has now certainly no longer a right angle like I've drawn here, which is a bit silly of me, but it's now quite a lot less than 90 degrees, and it's less than 90 degrees by more than the angle that was less than 90 degrees was in the seesaw shaped molecule. In other words, it's a smaller angle than the one that we said was less than 90 degrees in the seesaw. Here's a linear molecule. Again, not a specific example we need to remember, but if you're given xenon difluoride and you add up all the electrons in it, you will end up with a Lewis diagram that's got more than 4 pairs. It's got 5 pairs around that central atom. You shouldn't be put off by that. You should just say to yourself, right, okay, what shape will it form? And now, if you imagine here is our equator around the circle, and these are the 2 atoms at the poles. Okay, so the lone pairs take up positions around the equator. This angle here between the xenons and the fluorines is exactly 180 degrees, because although these are repelling the bonding pairs more than the bonding pairs did, they're all repelling them in kind of opposite directions by equal amounts, so they all cancel out, and this ends up being 180 degrees. Okay, I think that's all of them. It is. That's all the examples of the 5 electron pair shapes that we're going to look at, okay? And only one of them did you have to remember as a specific example. But notice what we've done by considering VSEPR, what we've considered how the bond angles will change from one shape to the next, okay? Hopefully you know the names of the shapes as well, and you understand what the bond angles will be like. Don't have to put exact figures to them, but if there's anything there that you want to comment or ask questions about, then please feel free to let me know, either by coming to see me or by posting a comment on YouTube.